Okay, this microphone seems to work. So good morning, everybody, and welcome. Thank you for coming to this morning's special ISWA colloquium. I'm happy to introduce Shancong Mou, who's a PhD student at Georgia Tech, finishing up this spring. He has been amazingly prolific in writing papers as a PhD student, something like 15 already out, including 5 Best Paper Awards or finalists for Best Paper Awards, so very productive. And so I'll just turn it over and take it away. Welcome.
Yeah. Okay, thank you. So can you hear me, especially who sit in the back? Okay, let me get started. Okay, so first, thank you everyone for bringing me here to give the talk of my research. So my research focuses on the AI/ML enabled data analytics for the complex engineering systems. So, sorry. Okay, so here is the outline of my talk today. So first, I will give a brief introduction of the motivation why I'm doing this research, and then I will talk about one of the research topics I have been exploring during my PhD study. And next, I will cover some other research topics that I have been exploring. And finally, I will give some the summary and future directions. So, sorry, I don't know what happened. Okay. Okay, so why I work in the field? So this is because this AI/ML enabled data analytics for complex engineering systems is very important in terms of national level priority. For example, if you look at those national strategies in the recent years, like the National AI Strategy and National Advanced Manufacturing Strategy, right? You can see there is a trend of the convergence or the merge between the AI/ML data analytics technologies with these complex engineering systems, including but not limited to manufacturing, healthcare, those kind of complex systems. And so that's why this is, let me just instead of here. So that's why this is very important and promising field to work on, right? There are lots of research and funding opportunities to explore. So here is a brief overview of my overall research area. So I work in the field of AI/ML enabled data analytics. And under this big umbrella, I have 2 research directions. So the first direction is related to system monitoring and diagnosis. So in this direction, I emphasize on the anomaly detection in high-dimensional data with methodological contribution, especially in the robust learning kind of methodologies. And so here are a few application examples I have been explored. The first one is the personal electronics manufacturing process quality control, and another one is related to medical imaging, the anomaly detection, okay? And the second direction is related to the system analysis, modeling, and design optimization. So under this direction, I have explored different topics. So the first one here is related to the quality improvement of the fuselage assembly process. So we have been adopting and developing methodologies from physical simulation and partial differential equation constraint optimization techniques to address the variation propagation reduction problem in the fuselage assembly process. So fuselage is one of the major mechanical, structural component of the modern airplanes. Okay, and the second direction, the second topic under this direction is related to the modeling and the control of complex engineering systems. So here we have mainly developed the physics-informed machine learning strategies. For example, with application in semiconductor manufacturing and also composite material manufacturing process. Okay. And the last but not least direction I explored a little bit is related to the stochastic system analysis, right? So this is mainly related to the scheduling, job scheduling problem of the data center. Right? This is also a very complex engineering system. So next, I will dive into the following research topic. It is actually the first one I discussed about. It's robust learning for label efficient and fine-grained anomaly detection. Okay. by the way, before I dive into the detail, if you have any questions, feel free to interrupt me. Okay. So what is fine-grained anomaly detection? Let me start from a quality engineering, quality control perspective. I think Dr. Liu is teaching this course, and some of his students may come here. So I would say, like, traditionally, the quality engineering, we focus a lot on the sample-level process monitoring. What is sample-level process monitoring? It mainly focuses on the process change detection based on the sample-level statistics, like sample mean, sample variance, right? Whether this batch of product is in control or not, right? But, thank you, I think I'm good with this. But the fine-grained anomaly detection is really, we try to look into the detail of the product at hand. For example, if your measurement signal is an image, then in this case, we try to identify the defects from a pixel level, right? What does this defect look like? What is shape, right? And this is a very important problem. Why? There are two reasons. The first reason is the opportunities, right? As process engineers, with the development in the sensing technology, such as the high-resolution camera and even like 3D point sensor, we do have the capability, or we do have the chance, to get a detailed product quality information from our measurement system. So this gives us the opportunity to look into the fine detail of our product. And the second aspect is actually the need, right? So with the increase of the value of our product, especially in these advanced manufacturing systems, precision manufacturing, right, there is an increase in the requirement for fine-grained quality characterization. So let me give you an example here. So in the project we work with the Apple company, we try to establish the monitoring capability for the pixel level, fine-grained monitoring of the product surface quality. So here you can see, instead of only care about whether this iPhone is defective or not, that means a sample level. Now we look into the localization level and even pixel level. What does those defects exactly look like? And what it is, right? So why we care about this? Because those kind of characterization directly relate to our profit. For example, if there's some like cleanable, like dust, right, then a very cheap cleaning process can deal with this problem. But if there really some scratch on top of your iPhone, right, then maybe you need some very complex rework kind of process to deal with it, right? So this kind of fine-grained detection result, right, directly decide what kind of decision we're going to make. And those decisions going to directly kind of impact our profit, right? So that's why this fine-grained anomaly detection is a very important trend, an emerging trend in this kind of advanced manufacturing systems, not only in these personal electronics. But I would say this is not a simple problem. There are several challenges you have to address. The first challenge is the limited anomalies induced by the high-yield manufacturing process. So as I mentioned, this kind of personal electronics and even semiconductor, right? Those are very, very expensive products. And in our manufacturing process, what is high-yield manufacturing? That means I can produce 1,000, 10,000 iPhone per day, but I may only observe 1 or 2 of those defective samples. If you have a little bit background in learning, right, you can see it's very difficult for me to use the data here to train a supervised model, right? So in this case, we have to adopt an unsupervised perspective to address this problem. Another challenge is directly related to what I talked before, the fine-grained defect characterization requirement. I don't have enough supervision signal, but my detection result is really high accuracy, right? It's like looking for a needle in a haystack. Right? Those are the two challenges, very common and very challenging problem. The third challenge here is the complex distribution of our data, right? We are dealing with the complex advanced manufacturing systems, right? Different products have their different signals. For example, those are the measurement signal, right, of the battery manufacturing process, wood, and even hot rolling process, right? You can see they may have diverse surface pattern, right? How do we model this signal is a big challenge. I will go to the detail in the methodological part. And the next challenge is the high-dimensional or high-resolution measurement. For example, in this application, we may get like 50,000 by 60,000 image That is just one data sample we have. This is very high-dimensional problem we try to deal with, right? And the last but not least challenge here is actually the domain-specific knowledge. So when we talk about we do have a lot of different products, different lines, right? Each product, each manufacturing process have its own knowledge, right? Like physical knowledge or our engineering knowledge. How to incorporate this kind of knowledge to further improve our algorithm is another challenge, okay? So, and those challenges actually call for further development of the fine-grained process monitoring capabilities. And my research, one of my research direction is to tackle this problem. So I have adopted a robust learning perspective with further innovations to address those challenges. For example, we have developed the distributional assumption-free robust learning method, try to tackle the complex distribution challenge we have. And we have also explored the data transmission and computation efficient robust learning method, try to deal with the high-dimensional data related challenge. And the last but not least one here is the domain-specific knowledge incorporation. So how do you incorporate the domain-specific knowledge, or in other words, the structure in your data into your algorithm, right? And make it like more accurate and better generalization capability, right? So this is the additive tensor decomposition method we have been working on. So because of time limited reason, I will focus on the first one in the following talk. Okay. That is distributional assumption-free robust learning for high-dimensional data analysis. First, what is robust learning? Right, let me give you a very brief introduction. Robust learning means, in this talk, right, is robust signal restoration under unknown gross corruptions. Okay? So, for example, you may have the input signals with anomalies, right? For example, you may have a scalar input with outliers. You may have anomalies in your functional curve measurement, and you may have corruptions to your image, right? And those are the unknown corruptions to my signal. Give me this as input. My goal here is to restore the clean signal. What I mean by clean signal is the signal before those corruption process happens, right? Once we can achieve this kind of signal restoration, a byproduct here is actually anomaly detection. One thing I want to emphasize here is those kind of anomaly detection is indeed fine-grained, right? I can directly compare the restored signal with the input signal, and the difference can be used for fine-grained anomaly detection. Okay, let's talk a little bit about the current literatures. Right, this is not a trivial problem. So here are three categories of literatures try to deal with this problem, especially the statistical robust learning field. So the first one is robust principal component analysis and its variance. So they focus on restoring a low-rank structure from the corrupted data. So the low-rank structure can be matrix low-rank or tensor low-rank. Okay, and the second category here is the smooth sparse decomposition kind of structure. They try to exploit the smooth structure in my data, right, and try to restore this kind of clean signal. And the last category here is the outlier rejection or robust regression type of algorithms. So they focus more on the signal that follows some simple linear kind of regression structure. And they try to develop a robust restoration procedure to restore this signal, right? However, right, if you look at the examples I showed you before, especially in those advanced manufacturing lines, the battery, wood, or hot rolling process, right, you can see the signal here, most of them do not follow those kind of simple statistical prior assumptions. Right? For example, look at the battery here. Right? It's no low rank, not smooth anymore. And the current method, it works. It's very popular, I would say, in the anomaly detection literature with application in advanced manufacturing domain. But you can see they rely on lots of the restrictive statistical assumptions. It do have difficulties, right, in dealing with those kind of complex signals beyond the description of the simple statistical priors. Right? And our objective here is to develop a distributional assumption-free, okay, robust learning method for the restoration and anomaly detection in complex signal. Here I give an overview of the method we developed. We name it robust GAN inversion, right? The main idea is instead of use, right, a pre-specified statistical price, like the low-rank smoothness or something else, we try to learn a description of the data, of the normal data we have, right? The intuition comes from the application problem we deal with. For example, in the iPhone manufacturing process, right, we do have, like, the challenge, we don't have enough anomaly samples, but we do have a large number of normal samples, right? Those normal samples may correspond to different operation conditions. But if we can learn kind of a structure from these normal data samples, then based on this learned structure, we hope we can achieve the robust signal restoration, okay? So there are two steps in the developed method. So the first step is the distribution learning procedure. So give us, based on a large clean signal data set, for example, the normal operation condition, you get a lot of the normal signals. And based on this data set, we try to learn a clean signal manifold, right? This is the first step. And the second step here is based on this learned manifold, right? Give me a corrupted input signal, right? I do not assume any prior knowledge of the corruptions. But sparsity is an assumption here. But other than sparsity, we do not put any assumption here, right? We aim to restore a clean signal from the learned manifold. And at the same time, right, simultaneously, we aim to find a corrupted region mask. That is a binary mask that's going to exactly cover this corrupted input image, corrupted region, right, by solving an optimization problem. I will go to detail in the following talk. But so once we can achieve this goal, right, there are at least two set of applications we can consider. The first one is signal restoration, right? Based on the restored signal, we can achieve missing value imputation, signal denoising, and image super resolution. This is a very important topic, especially when my measurement tool is limited because of the physical limitation, right? And the second application is really the corruption identification. The identified corrupted region can be used for anomaly detection. That's a very important topic in quality control. And the second one is foreground-background separation, right? Some of those have been used for human factor-related research. Is try to extract the human beings from a video I get in the monitoring. Then I'm going to use this extracted human being gesture to do downstream human factor-related research. Okay, and but in order to achieve this, there are several challenges to address. So the first challenge is, remember, we are dealing with a very high-dimensional distribution. How do we learn such a distribution, right? And the second challenge is, even though you're giving me the learned distribution, how do I achieve robust signal restoration? So I will dive into the detail of those two aspects. Okay, so the first challenge, we propose a generative modeling approach of the high-dimensional data distribution. Here, I have to use this a little bit. Let me see. Okay, our goal here, sorry, can you see my pointer here? Okay, so the goal here is to learn a pair 0 high-dimensional data distribution from the normal sample we have at hand. Okay, and a very common approach is to model this pair 0, right, high-dimensional data distribution as a transformed distribution from the low-dimensional Gaussian distribution. And the transformation is a neural network parameterized by this theta here, right? And our goal here is to learn this parameterization instead of directly learning this high-dimensional distribution, right? We try to learn, I would say, approximation, right, of the high-dimensional distribution by using a neural network and also with the low-dimensional Gaussian distribution together, right? A common approach to achieve this goal is through adversarial training, right? That is generative adversarial network. That is GAN, okay? So the main idea here is you have two networks. They got to compete with each other. The generator network is the one we are looking for, and the discriminator network try to distinguish between the generated data sample and the real data sample, right? Once those algorithms converge, we can learn a really good distribution we can approximate the high-dimensional distribution with very high accuracy. For example, here is a large-scale human face data set, right? And those are the images, right, generated from our learned distribution. You can see those human faces never exist in reality, but it really looks like real, right? So that means those kind of tools are very good at capture the high-dimensional distribution at hand, okay? And once we have this distribution, there are two things we can do. The first thing is sampling. What I mean by sampling is give me a code, latent code, in the latent space. As I mentioned before, latent Gaussian distribution, right? I can go through the generator here, right? I can go through the generator here to generate a sample in the high-dimensional space. And this data sample will look like real sample from the high-dimensional distribution, okay? And the second thing, more interestingly, is we call it gain inversion or restoration. That is, give me a high-dimensional data sample, right? I can find a latent space, right? A code in a latent space. So here, X, for example, X here is the input in my high-dimensional data space, and this Z is the corresponding latent code in my latent space. My goal here is to solve this optimization problem, to find the corresponding latent code. So this is called gain inversion, right? And the immediate question is, can you directly use this gain inversion algorithm for the robust signal restoration, right? That is, what if my X is corrupted, right? It's not clean anymore, or it doesn't exist on the manifold I learned, right? Can I directly use this algorithm to restore the clean signal? Okay, the answer is no, okay? So there are two reasons. The first reason is the robustness issue, okay? So here is a demonstration of the learned manifold of our target normal signal class, okay? This corresponding to our clean signal, the signal we want to restore, okay? The manifold. And this one is the corrupted input signal. I use wood manufacturing as an example. So if you can see, there are two defects, right, to my input signal. And my goal here is to restore a clean signal, clean background signal here. Once I can achieve this kind of background signal restoration, right, it's very easy for me to compare the restored signal and the input corrupted signal for anomaly detection, right? We can achieve pixel-wise anomaly detection here. But if you use the gain inversion algorithm, what you're looking for, you actually are looking for the closest point, right, on your learned manifold to the input corrupted signal. Right? So because of the existence of corruption, right, in most of the cases, the inverted signal do not overlap with the ground truth clean signal you care about. Right? This is what we call the robustness issue. Okay? Any question here? Okay. So this is what we call the robustness issue, right? But because of those robustness issue, if your restoration is this one, right? You can see there's wood manufacturing, right? Their characteristics are actually the circles here, right? Different wood surfaces have different circles, right? And you can see the circle, the ground truth circle we try to restore is the same as the input signal here. But the one, if we directly use, sorry, can you see? Okay. The one, if we use gain inversion algorithm, right? They have different circle structure, right? Imagine you do a pixel-wise comparison for anomaly detection, right? Any pixel that is different from your input going to be identified as anomalous defects, right? This is going to give you a very high false positive rate, okay? So this is one challenge. But what if we just ignore this robustness issue? There's some initial study showing that it achieved the worst performance, even on a very simple benchmark data set. Distribution gap. As I mentioned before, there is a high dimensional distribution, and we learned a distribution to approximate that distribution, right? There are always some gap between the learned distribution and the ground truth distribution, right? And this gap will lead to a distance between the restored image on my learned manifold and the ground truth image on the ground truth manifold. This, right? And this gap also contributes to the high positive rate of the anomaly detection result. Okay, right? So in order to address those two issues, the first one, we propose a robust gain inversion method, right? And we try to exploit the sparsity kind of characteristics of the defect or the anomalies in general in signal processing kind of aspect to achieve a robust signal restoration. And in order to mitigate the approximation gap, we propose to fine-tune the learned structure manifold towards the ground truth manifold simultaneously, okay? So first, let's go to the robust gain inversion. Okay, here we assume this high-dimensional distribution is well approximated by our learned distribution. Okay, or in other words, here we assume there is no approximation gap, right? And its corresponding engineering interpretation is, again, our model is trained on a large-scale normal signal data set, right? Collected from our manufacturing process that covers all the normal operation conditions, right? And the second assumption is the sparsity of our corruptions. Mathematically speaking, that means our corrupted region size, right, is much smaller than the ambient dimension of my input signal, right? So its corresponding engineering interpretation is the defects or the anomalies are sparse. So think about the iPhone kind of inspection process, right? The scratch, right, or the dirt, a very small portion of your whole image, right? So this is its corresponding engineering interpretation. So based on this assumption, we propose to formulate this signal restoration problem as a constraint optimization problem here. So in this, in this optimization problem, we have two variables to be solved. So the first variable is the z variable. So this z variable is the latent code on the learned manifold we try to restore, right? And this m variable is a binary variable that's going to directly cover, right, the corrupted region. And there x is the input signal with potential corruptions, right? If you look at this formulation, we aim to find the sparsest solution, right, such that the signal, input signal x, right, is the same as the signal generated from our learned manifold, but outside, okay, outside the corrupted region, right? And any questions on the formulation here?
What is the notation of the dot here?
Oh, okay, sorry. So this dot is element-wise multiplication. For example, x is a high-dimensional image, right? And this m is high-dimensional mask, right? Binary mask, corresponding to each pixel element. If there is a corruption, it's 1. If there is no corruption, it's 0. So the element-wise multiplication means 1 minus m, okay? If there is corruption, 1 minus m on this specific pixel or element is going to be 0, right? If it's 0, that means it naturally satisfies this constraint, right? If it's not 0, for example, if it's this term, 1 minus m is 1, that means I have to exactly satisfy this manifold constraint, okay? So this is the problem formulation.
You make it exactly match the manifold, and you don't, what if it was like epsilon away? Wouldn't that also be good?
In this, under this, okay, remember we have,
This one you're making it exactly.
yeah, in this, remember we have two problems to be solved. The first one is the robustness issue. The second one is the approximation gap. So when we solve the robustness issue, we assume our underlying model is actually the signal is generated from the manifold plus some sparse corruptions. So in this case, in other words, we assume, right, the signal is like, at least its clean part is on the manifold. And the next part we're going to discuss about like what if even the clean part is kind of deviated from the clean signal manifold. So yeah, I want to make sure everyone understand the problem formulation here. So yeah.
Just curious, will this simulation face the risk of overfitting? If in other words, in order to satisfy the constraint, will the z sometimes like overfit? In this way, your m can be like
less sparse.
Yeah, less sparse.
Okay.
Will that be happening?
Okay, yeah, very good question. Let me go to the intuitive explanation here. Okay, so look at this problem formulation, what we are looking for, right? So here is a corrupted input signal, right? You can see, sorry, I'm not sure, in the back, can you see those corruptions here? Okay, so this is a corrupted input signal, right? Instead of directly use the gain inversion kind of algorithm, or in other words, instead of directly seeking for the closest point to my input corrupted signal on the learned manifold, what we are looking for are the intersection of two manifolds, two subspaces. One subspace is the manifold of the learned target normal class. And the second manifold is the set of signals, right, that is consistent with possible sparse corruptions, right? And the intersection here is the background we are looking for. We are looking for the sparsest solution. That means as much as the background generated from the learned manifold match the input signal, right? We're going to keep it, right? And if it's deviate significantly from all the possibilities I can generate from a learned manifold, I will put a mask there, indicate there is a defect, right? And our key point here is we try to regularize the mask size. So I think Dr. Liu mentioned a very, very important problem. Imagine if I don't penalize the mask size, there will be a trivial solution. I will give this M all once, right? Then this is going to be trivial, right? So that's why we try to impose this kind of sparsity constraint. This also comes from the application problem we are dealing with, right? And there are lots of like the optimization experts sitting here, right? If you look at this problem, it's very challenging, especially minimizing this zero norm, right? And please keep in mind, the image we are dealing with is high dimensional, right? It can easily be like thousands, millions of dimensions, this problem, even solving this problem, right? So from an application perspective, what we do is we adopt a relaxation technique, right? That is, we try to first, we relax this zero norm here as a one norm, right? That becomes differentiable, right, in that case. And also, we put this constraint as a penalty term in my optimization problem formulation, okay? And so we try to solve this problem, right? And use the first order method, right? One reason we formulate it in this way is this GZ, remember this G is a trained neural network, right? My gradient, the gradient of this loss function with respect to Z is very cheap for me to calculate because it's already trained and it's already stored in my trained structure, okay? And by solving this problem, we hope we can get some good solution, right? One immediate, so at least this problem reduced the difficulty of solving it, right? But my immediate question is, what is the relationship between the solution of the original problem, right, and the relaxed problem, right? Or in other words, let's say even though I can solve this problem, problem 2 is optimality, right? What is optimal solution, or the restored signal and the identified corrupted region mask to the ground truth, right? So here we provide two justifications. The first justification is the asymptotic optimality of the latent code, right? Intuitively speaking, as long as our tuning parameter at the penalty term, right, goes to 0, becomes smaller and smaller, right? The restored signal will converge to the ground truth signal, okay? So this is the key for signal restoration. And another characterization is asymptotic optimality of the identified mask. Remember, we want to identify a binary mask, right? And under some mild assumptions, our solution, right, will converge to the ground truth mask as the penalty term goes to 0, okay? And more interestingly, this coincidence with lots of like the robust learning literature, right? There is a, theoretically speaking, there is a positive tuning parameter, lambda prime, right? As long as the magnitude of the lambda we use here, tuning parameter, is smaller than this threshold, we can just do a binary thresholding of our solution. It will be the same as the ground truth binary solution we have, right? So this is, right, is the key to anomaly detection, right? This is the key to anomaly detection. Okay. Any questions? Yeah.
So in the previous formulation, is that possible that in the like a latent space Z, you have two Z give you the same map? In that case, will during the match, because you care about the learning the latent space, if that happens,
yeah,
will the result be wrong? Or?
Okay. Yeah. Thanks for this question. So the result I show here, let me show you here, right? Especially it's like this, right? The convergence result of a restored latent code. But remember, our goal here is to restore the signal, right? So if 2z give me the same mask. That means those 2z going to give me the same signal restoration result. That is, 2z give me the same image, even though they are from a different point on my learned manifold. But this doesn't hurt my application, because what I care about is really the restored signal, not the latent code in my latent space. So this result actually here, I stated that like point-wise kind of convergence. Actually, what we have, the result is the solution set of Z will converge to the ground truth solution set, ground truth set of latent codes. Then gonna project to the same restoration signal we care about. So this is the idea behind. Okay. But in terms of application-wise, right, we don't really care about what latent code we restored. We really care about what is the restored signal after this G projection. Right? And this also relates to some assumptions. You can make assumptions like the inversion is unique, then you get the result. Okay. So let me show you some simulation study of this method. Okay. So as I mentioned, in the first step, right, we assume our signal, corrupted signal, is generated from a learned manifold, clean images, plus some sparse corruptions. And we use about like 25% of pixels corruption, and we're going to vary the corruption level from -1 to 1. So the reason is that during the training process, we already normalize the image in between -1 and 1. So this is the largest magnitude you can have in the corruption. And here is the result. So the y-axis is the restoration error. That is the difference. Give me a corrupted input image. I'm going to restore a clean background. So this is the difference between my restoration and the ground truth clean image. And the x-axis are the corruption levels from -1 to 1. And there are 3 different curves. So the first 2, you can see the blue curve and the orange curve are the traditional GAN inversion algorithm corresponding to L1 or L2 loss. And the green curve is the robust GAN inversion problem formulation. You can see we get a relatively stable performance across all the different corruption levels. But one thing I want to bring your attention is you can see when the corruption level increased, the solution get a little bit worse. So this is related to the optimization procedure of a highly non-convex optimization problem. We cannot always guarantee every time our solution go to the global optimal. Okay. Okay. So after the first step, the next step we're going to deal with the gap. That is, what if my underlying truth signal, right, like exists outside the learned manifold, right? So here, in order to address this problem, this is more like engineering kind of driven or empirical. We propose a mask-free generator fine-tuning step. That is, at the same time of solving this latent code, this mask, right, we fine-tune the trained generator or the learned manifold towards the ground truth manifold. Right? In the application problem, we observed the positive result here. By doing this step, we can further improve the restoration quality. Okay. Okay. So here is a brief discussion of the proposed method and its connection to the traditional robust learning literature. Right? I would say this method roots in the robust signal processing method. Right? But instead of using those kind of restrictive statistical assumptions, we propose to learn a deep generative prior, right, to describe the signal we want to restore. This, from one side, comes from the engineering practice we care about. From another side, we try to generalize the existing robust signal processing methods to a larger class of generic signals. This is one aspect. Another aspect here is this method has deep connection to the robust statistics. If we adopt a 2-norm loss function, then our loss function becomes separable pixel-wise or element-wise. So I show one loss term here. If you are familiar with those MS meter literature, you can see it shares similar structure as the MS meters, right? The loss becomes very deep when the magnitude is small. The loss becomes kind of like smooth, like more like the slope becomes small when the magnitude becomes large, right? So that's why intuitively it shares, or it's kind of inherent, the robustness structure to outliers. Okay? So that's why we call this method the distributional assumption-free robust learning method. for the complex signal restoration and anomaly detection. Okay, next, we have talked a lot about the methodology we developed, right? But as I mentioned, my background, I come from application. We try to solve very important application problems. So here I will show two examples. There are two aspects. One thing is signal restoration. Another aspect is anomaly detection. So there are two examples. Let me see, what time is it? Okay, there are two examples. The first example is corruption identification, or we call it answer-wise, pixel-wise anomaly detection, right? So here are some defective samples from a standard data set. And you can see, can you see on the back, can you see the defect structure here, right? I would say it's a little bit difficult even for our human beings to identify, right? And our goal is to find the defective region, like this ground truth here, right? And we compare with several benchmark methods, not only in the statistical robust linear literature, but also the state-of-the-art deep learning-based unsupervised approach, okay? Here is the result. So the first column are the input image or the signal with the corruption or the defects here. Our goal is to restore the ground truth defect mask. And the third column here is the proposed method, right? And the fourth column is the most advanced robust learning literature result. You can see their result is not ideal because the lack of the modeling capability of the complex signal, right? If it, so like, how many of you have a little bit background in robust PCA? So robust PCA try to deal with the linear structure, right? But what if, if I put all of those images together, the matrix not kind of linear structure, right? So that's why performance is poor. And here is a patch core method that's kind of like a deep representation-based method. They lose the pixel-wise accuracy of tracking the defect. And the last, the last two here are actually the deep reconstruction-based method. It shares the similar intuition of the gain inversion. But again, because it doesn't have any robustness incorporated in the algorithm, so you can there restore the signal will be, even though on the learned method, but it's not the same as the ground truth we care about. So that's why they have a lot of false positives. Anything that is different from your input is identified as defect. So once your restoration is a mismatch, this is going to be a disaster. Okay, so that's why I would say like the proposed method is combines the best of both worlds, like both the deep learning kind of literature and also the robust learning literature. So that's why we outperform those two methods. Okay, so another example application is the signal restoration. So here it named semantic image imprinting. Our goal here is to restore the signal under unknown corruptions. So here is an example. So there are input human faces, right? And those here are the unknown corruptions. Even though we put in the center, we don't assume we know these corruptions. Our goal is to restore the ground truth human face, right? And this is the input, this is output, this is our goal. Right? And here I show several results. So here, this one is the restoration performance of the proposed algorithm, and this is the restoration performance of one of the state-of-the-art method. Most of the current signal restoration methods, especially for those kind of highly nonlinear kind of complex image signal, they are reliant for the based on the generative model. And their key assumption is they assume they know where are those corruptions. Once you know the corruptions, the restoration problem becomes a little bit trivial, right? You don't have to solve two parts. Once you know that part, then you only need to deal with the restoration. But if they do not assume they know this like the mask, that's their result. You can see the restored signal will kind of overfit the corruptions in the manifold. And this is the best possible result you can do. That is, we fixed the mask, right? You fix the mask, you only solve for the ground truth clean signal, right? In this case, the restored signal from our method is very close to the best possible result we have. Okay, so here is a brief summary of a proposed method. From a methodological point of view, right? This is a non-trivial generalization of a statistical robust learning literature, right? And it's an initial attempt for the distribution assumption-free robust learning. And here are some practical applications like the signal restoration anomaly detection And there are lots of future directions to explore. For example, there are lots of beautiful guarantees in the traditional robust learning literature. So can we establish those guarantees for this kind of learning-based restoration structure? And also, can we incorporate other kind of prior structures into our algorithm to achieve better performance? Okay, so next I will spend several minutes to discuss other research topics I've been exploring during my PhD study. So they are quality improvement for composite fuselage assembly, physics-informed learning, and also stochastic system related. Okay, so some of you may be aware that in the year 2022, the Boeing 787 production got a serious delay because of the gap issue during the assembly process of our fuselage. Our fuselage are those big, like circle type structure in my assembly process, and those are nowadays they are more and more used the composite structure. Okay, and the current practice to address this gap issue is to put actuators right along the edge of my structure and generate push and pull forces to control my structure to its target shape, such that I can reduce the gap. Right? The current practice is to rely on the very experienced engineers to determine how much force you're going to apply on this structure. It is not that optimal or efficient. Right? So our objective here is to quickly generate the optimal force for each actuator, and then we can achieve the best dimensional shape control. So here is a brief overview of the developed method. So we try to exploit two sources of information. One information is the online measurement. That is, we put a very accurate measurement device to measure the 3D shape geometry. And another input is actually fuselage design information, because this is a manufactured product. Right? And the manufacturers do have its mechanical property encoded as like the parameters here. Right? Based on those two sources of information, we're going to build a simulation, and then we build a like PD constraint optimization kind of problem. We aim to find the optimal force applied on my structure such that the shape after control is as close as to target shape we care about. Okay, so we have made several contributions in this field. And another thing is physics-informed learning. So in terms of manufacturing complex engineering systems, right, like composite manufacturing, composite material manufacturing, electronics coding, and even like the semiconductor manufacturing, right? Those are complex engineering systems are governed by physical or chemical laws. It's actually a set of PDEs we care about. There are two extremes. One extreme is we don't have data, but we have full physics. That's related to the fuselage simulation I talked before. And another extreme is the big data, but no physics. That's like the learn deep prior in my first topic. But most of the engineering problems, we do have some data, but we're going to spend more and more effort in collecting more. And another aspect is partially known physics. How to optimally integrate those two sources of information to build a better model is very important. Keeping this in mind, we have done a serious work. Here, depending on how much knowledge, physical knowledge you have, and how much data you have. Try to explore the data structure in your problem and the physical structure in your problem. So those are the three works we have been done with application in composite manufacturing, semiconductor manufacturing process, right? And last but not least is the data center network scheduling. So I have made a little bit exploration in this domain, right? Data center is very important. That supports our nowadays machine learning practice. So the very important problem is that scheduling problem, okay? So we have studied this heavy traffic problem for the scheduling, okay? And this is some results we have, but I will not go to detail. Now, let me go to the summary here. Okay, I work with data. So those data come from very important application problems, right? And so based on those challenges from different application problems, we further develop the methodology to address the challenges and generalize this methodology to different application problems, okay? And here are a few future research directions I would like to explore. And this is the examples of potential funding resources I can explore in the future. And the last topic, teaching, I will be very flexible in teaching different courses in the undergrad level, grad level. And I will be also very interested to develop my own course, like the physics-informed learning related courses. I have been developing a guest lecture series for a PhD level course in Georgia Tech. I hope I can further expand this course into a formal course in the future. Okay, so thank you. So here is my overall talk. Feel free to let me know if you have any questions
Okay, thank you. Actually, before questions, I want to take the prerogative to ask my own question. I would actually like to hear, I know we're aware of the time, but I'd like to hear a little bit more about your research directions. Could you spend a little more time on that slide, and then we'll have more questions on that. Yeah.
Okay.
Thank you.
Okay, so here are a few research directions I would like to explore in the future. One is the related to process monitoring diagnosis, right? So this, I focus more on the scalable and efficient algorithms, especially for our data challenges, the imperfect and massive data under complex correlation structure. You can see a lot of my work try to deal with or exploit the structure information in my data, right? And another thing I'm very interested is the system modeling control optimization based on this domain principle informed learning approaches. I have the undergrad background in I would say energy power engineering. It's more like the computational flow dynamics heat transfer. So I'm very interested to integrate this kind of physical information with the data and build better models. So those are the fundamental research opportunities I would like to explore in the future. And here are an example of applications, right? Including but not limited to. The first is personal electronic device manufacturing, right? This is very important direction to work. I mean, nowadays, our industrial engineering researchers do not really get very deep into this field. But in the future, in the next few years, this is going to be a very important field to be worked on. If you think about advanced manufacturing, right, there is a trend of manufacturing the high-quality, high-value products, precision manufacturing, like the personal electronics, even medical devices, right? That's one thing. Another thing is the large and flexible parts assembly process, right? I have been working with the composite structure for the airplane, right? But those parts are very common in automotive industry and even the aerospace industry, right? And I'm also interested in the renewable energy systems in the future, right? And the last is I'm open to collaboration with different faculty members, right, as domain experts. And those are the fundamental and applications I would like further explore.
Okay. Thank you.
Thank you.
Yeah, so Kaibo, we can go first.
Yeah, regarding the work you mentioned, I think the idea is cool. You show some really good results, but I wonder how you train the Lambda. I guess the Lambda is the key, right, to ensure the good results. Yeah. Especially you talk about you have a very limited those faulty samples. So when you train the Lambda, how many faulty sample you needed in order to get a reliable Lambda? This is one of my questions. Second is how could you ensure this learned Lambda is generalizable to a wide range of those faulty classes? I know it can detect those known faulty pretty well, but how can you make sure it's generalizable? Yeah, these are two questions. Yeah.
Okay, let me repeat your question, make sure I understand. First thing is how to choose Lambda, yeah, right? The second thing is how to what is the generalization capability of the algorithm, right? Okay, so for the first one, I'm going to answer this question from two aspects. Theoretically speaking, right, if our manifold is ideal, the learned manifold is good, then there is a positive Lambda, not zero. There exists a Lambda. As long as you set your Lambda below this threshold, you get a very good result, especially for the mask identification. You get a very good mask here. Once you get a mask, you fix the mask, you achieve perfect restoration. This is from theoretical speaking. However, right, from a practice kind of point of view, it's not that ideal, right? There is a hope that it's a Lambda, but you never know what it is, right? So in order to do this, we really rely on the cross-validation here, right? There are two different approaches to do cross-validation. Remember, in order for this algorithm to work, right, what is the assumptions? Sparsity assumption. One is the signal comes from the manifold. Another thing is the corruptions are sparse, right? We do not put any assumption on the geometry or what does those defects look like, right? It can be a scratch. It can be a dust, pile of dust, right? As long as it satisfies the sparsity constraint assumption, our restoration performance will be good, right? So in this case, either we use a few number of real samples to train the algorithm, or we generate synthetic data, right, to train the algorithm, to do cross-validation. So I would say this data is not involved in the training process, right? So we do not overfit to the special case of defect geometry. So this is the key difference of the supervised approach and the unsupervised approach. This also relates to the generalization capability of the algorithm, right? So we adopt the unsupervised approach, right? Once we select a good lambda here, right? The good, for example, I generate a set of like synthetic data, right? As long as I get a rough number of how sparse my defects are, I can do a cross-validation to get the lambda. Once I get lambda, this algorithm will not be sensitive to the defect geometry, right? As long as the defects are sparse. So that's why it do have the generation capability, especially for the application problem we care about. We never know what kind of defect gonna happen in the future, but as long as it's kind of sparse, then we have the hope to restore it. Hope this.
Shi, you, I think, has a question.
Thank you. I have two questions. The first question is actually in deep learning area, there's a lot of work on image-based anomaly detection.
Yeah.
So what's the key difference of your approach? You are one of the deep learning-based anomaly detection with the existing methods. That's the first question. Second question is in your second step, you want to recover the underlying true distribution. This is the fundamental goal for all the GAN-based distribution fitting methods. So you seems like you want to adjust your GAN network based on single sample. So you must add some constraint on your theta, right? You cannot freely adjust the theta. Otherwise, you will be overfitting for the specific sample. So what are the constraints you add on the theta?
Yeah, thanks for your question. So there are two questions. The first one is you mentioned like this GAN network, right? There are lots of work in the image processing field and GAN inversion related literature, right? What's the difference of our proposed method, or in other words, what's our innovation here? That's the first question. And the second question is like in the inversion, especially the fine-tune procedure, right? How to restrict this fine-tune procedure, make sure we do not overfit to the input. Okay, so for the first question here, I would say the traditional GAN inversion or generative model inversion literature, right? They do not consider the existence of the corruption in your data. So most of them will focus on give me a clean image. I restore it, GAN inversion, either through the optimization-based inversion literature, or you can train another inverse mapping network to invert it. But their focus is more if I can restore the signal or not. But under the assumption, there is no corruption, or I know exactly where is the corruption. Right? But you can see those two problems are, like theoretically speaking, they are set the same. Right? Once you fix the mask, the restoration procedure is exactly the same. But what we care about is use this kind of GAN inversion algorithms for anomaly detection. In this case, you can never assume your anomaly is known beforehand. Once you know this is not anomaly detection, right? This is kind of a contradiction. So that's why we care a lot about the robustness in terms of GAN inversion literature. I would say we are the first several attempts try to exploit this deep generative prior in robust signal restoration, even in the deep learning literature field. And related to the first question, you also mentioned there are a lot of literature in like image processing for anomaly detection, right? I would say most of them, the successful, like in the last decade, we see a lot of successful stories of computer vision for anomaly detection. Most of them relies on supervised algorithm. The supervision is very important for them to get a very good anomaly detection result, especially when you talk about the pixel-wise, or not only for the image, right? The algorithm can be used for 3D point cloud functional signals, right? The supervision signal is the key element for you to identify the fine-grained defects. However, in our application, we do not really get this kind of supervision signals. So that's why we try to explore this kind of unsupervised structure here. But the unsupervised structure, as I mentioned, so there are some unsupervised exploration in deep learning field as well, but they are not ideal. Either they lose the resolution or their reconstruction results are limited. So we are the state-of-the-art method right now for this specific topic. So this is the first question. And the second question here, let me go to this slide. The second question here, the fine-tune, right? That's a very important step to ensure the solution quality of your result. So instead of explicitly incorporate the constraint in the object function, we restrict the fine-tuning steps and also its step size. So fine-tune is a very mature kind of procedure in the domain adaptation or other kind of deep learning literature. The key point here is you cannot tune it for infinite many steps. Then this thing gonna overfit to the incoming corruptions. We actually treat the fine-tune steps as a hyperparameter in our algorithm, and then we again use cross-validation to get the optimal fine-tune steps and the step size. So hope this answers your question.
Okay, as we see people are needed to go. So I'm sure there's many more questions, but in the interest of time, I think we'll wrap it up here. Thank you one more time, and we'll have other chances for questions for you later.
Yeah, thank you. Oh, so I think that's totally fine. Yeah, thanks so much for hosting this.